All right, so back to the live action. How do we calculate EX10 minus and EX20 plus? And we know, of course, we know EX10 plus. That's the amplitude of our wave that we started with. So if we think of the boundary, I'll draw it over here. Here's a boundary between 1 and 2. The electric field is in the x direction. There's Z, and of course H is coming out of the page. The electric field's here. So on this side, we have the incident and the electric fields. And because we're evaluating at Z equals 0, the exponentials in the fields disappear, and we're just left with the amplitudes. So we have on this side the amplitudes right along the x-axis for Z equals 0. On this side is E10 plus EX10 minus. Now what do we have on this side?
E plus X2 naught.
Right. Now, right here on the boundary, X, the electric field is tangential to the boundary. And what we know at boundaries from the previous course, ELEC311, is that the tangential components of the electric field have to be continuous at the boundary. Therefore, this sum has to be equal to what's on the other side, and that gives us the first condition. EX10 plus EX10 minus equals EX20 plus. So that's tangential components of the electric field, and I'll call that tangential E's. And they are continuous on the boundary. Now, we also need to do the magnetic fields, amplitudes. So to do that, we take the amplitudes and divide by what?
Eta 1.
Eta 1 on this side, eta 2 on this side, but we can't forget that this amplitude has a sign flip. So we're going to have the same as this. We're going to have tangential H's. So the tangential components of H are continuous at Z equals 0. So Sam, would you like to write down the second equation?
I would have to write down the second equation. Do you want to write in terms of E?
Yeah, in terms of E. So we have
divided by eta 1 minus X10 minus divided by eta 1 is that divided by eta 2.
right. So now we have to somehow figure out what to do. Let's solve for x20 and plug it into this equation here. So do you want to do that?
Solve for which one again?
So solve for x20 and plug it into that one.
Oh, okay.
So just say what you're doing here to get this, and then put the result in here for x20.
Well, in fact, I just moved this over there, right?
Right, that's right. So you can do that in one step.
Yes.
So
EX1 naught plus EX1 naught minus is this with the eta
2,
sent
yeah.
to that side. So eta 2 of this term minus this term.
Right. Now, here's the big challenge. I want you to solve on the fly for, carefully, EX10 minus in terms of what we know, EX10 plus.
Wow, that's a thinker. How do one do that?
Well, just straight algebra, so I don't know the best way to do this. I think the thing to do is to take the X10,
Just
bring
put it-
that over,
yeah.
and take the other guy and, so
Yeah. EX10
into 1
1
plus
eta 2 over eta
1.
1 of EX10.
Oh, we
Oh,
got
wait,
the X,
oh,
you
yeah,
factored it
factored
out
out, yeah.
already. So I think that's it for that. And now we have
Then that EX10 plus
into
of
eta 2.
2 over eta 1 minus 1.
All right, now,
Do I get 100% on that?
well, no, you have to finish.
Oh.
So we have to solve for x1 naught.
Mm-hmm.
So I suggest you put this over a common denominator, both of them, and then the eta 1's will cancel. And then you
Wow.
can solve for this, will be some multiplier times that. So let's see what that multiplier is.
Let's see what it is. Let's continue here. So you want eta 1, multiply eta 1 on both sides,
Yeah,
and then solve for
eta, yeah. So multiply eta 1 all the way through,
mhm,
and then divide to get e of x10. So
Wait.
multiply through by eta 1,
Oh, okay.
and then divide. So take it in pieces, eta 1, e x10 to 1 plus. Well, that's
Yep.
good.
Oh,
Yeah,
right.
yeah.
We're gonna run out of space
To
pretty
the
quickly.
minus 1, so 1 over that. No,
Wait.
that's right. No, you're doing
Oh,
it fine.
yeah.
Equals.
Eta 1 x10 plus.
Okay. Okay, so that's
So-
good. That's actually great. So
You like that?
yeah, I do like that, because look what happens here, and we'll see it on the next board. So what's going to happen is when we bring the eta 1 here, multiply it through, we're going to get eta 1 plus eta 2 there.
Beautiful.
And that's going to go in the denominator. And then we're going to get eta 2 minus eta 1 there. And then we'll solve it algebraically, and we'll see it in the next board. So rather than getting rid of the entire board, why don't we just erase this part? See if we can do that. So we won't use water, because it'll get kind of mushy. So let's just try to, well, maybe we need a little bit of water. Not too much, though. Okay, you can work on that. I'll work on this. We'll keep the other equations. Boy, it's a bit tricky. Hey, wait. That's good. We're all good here. It's all going to be fine. Oh, boy. This way we don't have to rewrite stuff, and you can see it right away.
That is beautiful.
Well, not yet, it isn't. We still Oh, man. It's
I swear, this algebra is so hard.
Yeah, more ways than one. The more algebra, the more erasing we have to do. Okay.
I bet they didn't learn it in high school.
No. Okay, so you want to solve for x1?
So you put in the eta to get EX10 minus eta 1 plus eta 2 equals EX10 plus eta 2, because this cancel out, minus eta 1. And then you
Divide?
put it on both sides. Do you want this to be on the top or this to be on the top?
No, I want to solve for the reflected.
Oh, just that, okay. that equals x1, 0 plus of eta 2 minus eta 1 over eta 1 plus eta 2.
And we've seen that before.
Looks very familiar.
This is our reflection coefficient.
Everything comes back together.
Yep, we had this before. ZL minus Z0, ZL plus Z0, where Z0 would be like this, or actually two different transmission lines, Z01 and Z02,
Yeah.
where they join. Because it's not really a load. The wave is going on and on.
Just keeps going.
Keeps going. So this is times gamma. Now
Now it's beautiful.
Now, what's really nice is we already know we could do the algebra, and you can, but it's much easier for the transmission coefficient. We know what that is from transmission lines.
1 plus gamma.
1 plus gamma. And I think you can do that. It's fairly easy. It's 1 plus this factor, and you get 2 eta 2 over eta 1 plus eta 2. Wow, so there it is. We've got gamma, we've got tau. We see that it's the same as transmission lines. No surprise there. And now what we can do is we can analyze the results, look at different situations like opens, shorts, whatever we can do, and a perfect reflector. So for example, if eta 2 is a perfect reflector, so a perfect reflector is a perfect conductor.
Wow.
So that means eta 2 goes to infinity, goes to 0. So because it's got 0 impedance, perfect conductor.
Wow,
And
so it's like a short circuit.
It's like a short circuit.
Okay, what happens if it's an open circuit? What's the open circuit analogy?
There is no open circuit analogy because you'd have infinite impedance. So I don't know what that is. You have a material that's infinitely resistive, which is physically impossible. So let's look at these different cases, and we'll look at that as applications and connections with the equations. So for example, we are going to have standing wave ratio again.
Wow, students love that.
And we have gamma. So all the stuff about nodes and locations of maxes and mins carries forward. And also, what else carries forward?
Everything.
But
What
something in particular. Our friend, the beautiful chart.
Smith chart.
That
Not the
means-
Smith chart.
Yeah, we can use the Smith chart to solve a certain class of problems using what we just learned.
Wow, this is amazing. And it's not like students would just forget what they just learned, right?
No,
so
it
they don't need to
refreshes
relearn
it.
all these.
They don't have to relearn it. We just have exactly the same as before.
That sounds great. So students will do very well on the next test.
Yeah.